All right, thank you very much, and great that so many of you transported themselves here for this talk. And before anything else, I'd like to express my gratitude to the organizing committee for the opportunity of giving this talk, to IPAM UTL for hosting this long program, the German Academic Scholarship Foundation and the Max Planck Society for their support throughout my studies, and Max von Renesse for his support on this project that I'm about to present. That being said, let's start from the end. So let's start with the entropically regularized quantum optimal transport. It's already been discussed on Monday by Lorenzo and Nata, authors of the articles I'm heavily relying on. But nevertheless, I'd like to restate the primal problem that I want to solve. So we're in quantum optimal transport. We have quantum marginals given, and we're looking for a quantum state on the product state so that it essentially minimizes energy with respect to a given Hamiltonian and some regularization term. In this time, I want to consider the von Neumann entropy. So this is essentially minimization of free energy. So whenever there's something that is unclear, feel free to interrupt me at any point. And that is what I'm planning to do. First of all, I would like to briefly review the duality result that's already been presented on Monday. And with that, I'm already able to describe my algorithm up to step size, which I will determine right afterwards. And in the very end, I want to have a result leading to the linear convergence of this method. So this is in the very end. But before that, where I want to build up, again, repeating the Sinkhorn algorithm that's also been discussed already, which then hopefully will motivate why one could also look at the dual functional from a different perspective to then get strong concavity. And then just before proving the convergence, I will show you the spectral bounds that I essentially need to have all this machinery working that I also took from a paper written, for example, by Lorenzo and Natalia. All right, in the very end, I'll have some nice pictures, hopefully. So let's start. I talked about the primal problem, and in this case, we have a nice dual problem for this. So instead of having this high-dimensional semi-definite problem, we can instead look for Kantorovich potentials U and V that don't have any definite constraints. And then we can maximize the dual functional that's given here. So that's pretty nice because it's also lower dimensional. And this basically forms the basis for algorithmic approaches to this problem. And now we can come to the first part of the title, to the dual block gradient ascent.
Just a question, why do you use this plus epsilon?
The plus epsilon, I mean, for the optimizers, it doesn't matter whether you have a plus epsilon or not. But if you want to have that the maximum of the dual is the minimum of the primal, you have to have this shift. Otherwise, you would have this gap.
Because it's not a -1 in the first formula. we will write in x log x minus 1 equal x log x, and the minus 1 becomes it.
All right. So it does not make a difference from the algorithmic perspective, but in order to be precise, we should have this. All right. We have the wonderful duality result, basically indicating that from now on we can forget about the primal problem. And for most of the rest of the talk, I'll only talk about the dual functional, because we can easily translate solutions for the dual problem to solutions for the primal problem. All right. So, dual block gradient ascent. For that, we would need to know what the block gradients are. And luckily, we're able to write them in closed form. They're basically given by these formulae. In this case, I'm using the opposite convention of what Lorenzo did on Monday. So if I now write trace 2, it means that I trace out the second system and keep the first. And given these block gradients, one can then formulate the algorithm I want to talk about. So we need to initialize our candidates for the convergence potentials somehow. And from there, I basically want to do just alternating gradient ascent in one variable and then in the other until we are sufficiently close to an actual solution. And then we can, in the very end, translate it back to a solution to the primal problem. So there's not much magic going on, and there's only 2 constants left to be determined. These are the 2 step sizes that we want to use for this algorithm. And how to do that? For that, I want to look at derivatives of the gradient. And for this, there is luckily also a closed form, which is, in my opinion, not that nice for computations. But at least we can write it, and we can deduce some results from it. So if we take a directional derivative of the dual functional into some direction A, we basically get a differential of the matrix exponential in the direction A tensor identity. And with that, we're in a pretty good situation, because given that we can bound the spectrum of this operator U times identity plus identity times V minus C. So if we have a bound on this, we can also have a bound on this derivative of the gradient. And if we have this, we in particular have a formula for our step size, which we can choose. And then we also have an estimate for the improval and the dual functional. So maybe that's worth writing down. So if we do one of these block gradient steps, we recover the original value of the dual functional, and we get some constant times the square of the norm of the first gradient of our dual functional. And similarly, you also get this for the other variable. So if you then do the other gradient step, you get u of d of un plus 1 vn plus 1 is greater or equal to d of un plus 1 vn plus some other constant times the square of the norm and in this case we want to evaluate this at un plus 1 vn. So whenever I write some capital C, it is just some positive constant. You can make this exact, but to ease notation, I just stick to these. All right. So once we have this, we can, from this, deduce an estimate for our improval in 2 of these steps. So we got that if we do 2 of these block gradient steps, we get what we had initially, and then something that depends on the norm of the gradients of D. All right, but now we evaluate these gradients at different places. So the one is evaluated at un vn, and the other one is evaluated at un plus 1 vn. So I want to synchronize this. And for this, we can also use these estimates to see that if we look at the gradient at un plus 1 vn, this is bounded by a constant times the norm of the first block gradient of D at un and vn. If we choose a fixed step size as given there, and then I want to square this and write the constant on this side. And then once one combines these, one gets that. When taking 2 of these block gradient steps, we have an improval of essentially the square of the norm of the gradient at un plus 1 vn. All right, so given that, one could already argue that this method converges, but I want to get a slightly better result. In the end, I want to have a linear rate of convergence. And for this, one somehow needs a lower bound for this expression here. So the squares of the norm of the block gradients. And that's what I will do just after going back to the original Sinkhorn that was already presented on Monday, and which forms somehow the basis for all of these considerations. So what has been done? Sinkhorn algorithm is essentially the same as the dual block gradient algorithm, except for instead of doing gradient ascent steps here, we just directly take the optimal value for the partial problem that is only in one variable. And this somehow led to some considerations that I expected that this is somehow, well, initially a non-trivial problem. And I just consider what would happen if one is happy with just improving the dual functional, not in the optimal way, but in some way, instead of solving this optimization problem, where potentially some effort might be, so computational effort might be put into some place where you optimize a problem that is not that closely related to your original one. But actually, there's one step missing here, and that is the renormalization step, where you basically shift the convergence potentials to make them converge. Why was that necessary again? Because the dual functional doesn't really see these shifts. So when you have any real lambda, you can shift one convergence potential in the direction lambda times the identity and the other one in the other direction. And this will leave your dual functional value invariant. So this is not nice if you are on a way to essentially proving strong concavity to be able to bound this, because, well, it is constant in one direction, so it can't be concave. I mean, it is concave, but it's not strongly concave. So this is an issue, but one can resolve this by looking at the dual functional in a slightly different way, because one notices, well, it only depends on this quantity here. As I said, shifts in opposite directions leave it invariant, so it is essentially a function of u times the identity plus the identity times v. And with that, one can also see this dual functional as a function not on the product space of the two spaces of the bounded self-adjoint operators of the convergence potentials, but on this space, which I'll denote G, which is a subspace of the space of bounded self-adjoint operators on the product space. And with that, we're in a different space. We have different gradient structure. So the gradients look different. And indeed, if one computes the gradient of the dual functional in this space, given with this inner product that is basically inherited from the space of the self-adjoint operators on the tensor product of the Hilbert spaces, one gets this expression for the gradient. And in particular, one can see that in the norm.
We just shift it and write it higher because it might be.
Okay, yeah. So keep this in mind. So if we take this gradient now on the space G, then in the norm squared, this is less or equal to the sum of the squares of the norms of the partial gradients. For all UV. Which is basically just computation, and then you get this result. And as I said, I want to derive strong concavity. So now I'm looking at derivatives of this gradient. And basically, you again get a differential of an exponential function. Whoop. Over here. So you can again employ the same trick. And this time in the other direction, if we have a lower bound on the eigenvalues of this operator, we have that D, when viewed on this space, is actually strongly concave, which is pretty good for convergence analysis, because if you have a block gradient ascent method, you basically need Lipschitz continuity of the gradient and strong concavity, and this already gives you a linear rate of convergence. Yeah. But all this relies on the bounds on the spectrum. Which I haven't proved yet. But luckily, this is also already given in a paper that has been partially presented on Monday. Namely, you can give bounds on your operator that are written like this. So it somewhat depends on the dual functional and your problem parameters. And then you basically need to invert two different functions suitably. And I hope you will forgive me for showing you some explicit content. But if you somehow want to have closed formulae for the functions that I'm referring here as nu1 and nu2. This is written here in terms of the Lambert W function. But for all computational purposes, I found that this is not really practical to do because in practical applications, your arguments of the W function are too close to 0 to effectively compute the inverses of these functions by this formula. All right, so let's maybe go briefly through the proof for these bounds. So for this, I use a spectral decomposition of this operator. So we have the eigenvalues kappa j and then the eigenvectors psi j. And now, for notational purposes, I want to have them in order. So start with the smallest and end with the largest. And then basically our dual functional can be rewritten as follows. So this is basically just it divided by epsilon. And then basically here on the right-hand side, you can directly evaluate this expression here because we have the eigenvalues of this operator already given. So we just need to plug it into the exponential and then sum it. On the left-hand side, we have an operator that almost looks like it. So we subtract c here and then add it again. And then one can basically also simplify this expression. And then you can basically estimate all of these kappa j's by the largest one, noting that essentially if you sum up here over j, it is just the trace of a quantum state. So it sums up to 1, and then it is all bounded by kappa d. And you can also trivially bound all functional values of the exponential function by 0. So that's lets you get rid of all but one term here, and the rest stays the same. So rearranging all of this, one gets this expression. So then one inverts the function that's written on the left-hand side. You basically get the bound as promised. For the lower bound, it's quite similar. I again use a spectral decomposition and rewrite the dual functional as before. And then essentially, as I said here, this is a trace of a quantum state. So this is a convex combination of all the eigenvalues of this operator. So one can bound this by taking the smallest eigenvalue of rho times sigma, and then 1 minus this for the largest eigenvalue. And with that, one again gets an inequality that doesn't look as nice, but here again we have essentially then a bound for the smallest eigenvalue. Now, provided that we already have a bound for the largest eigenvalue. Okay. So with that, we have this. Well, not quite. Yeah, just want to review how the dual functional in the two different domains looks. So in the original setting where one actually sees it as a functional on two variables, we get the Leibniz continuity of the gradient, but we couldn't get the strong concavity due to the degenerate direction. That luckily could be solved by basically just viewing D on a different domain. But by doing this, we have the problem that now we're not a block gradient ascent method anymore when we're using this algorithm. So this is only a block gradient ascent method when it looks at these variables, but it's not on this space. So one has to come up with short computation that I'm about to do. Yeah, sure.
Dual functional is a restriction of a function defined in the product on operators which are of that form, U sum B.
Yeah.
That you cannot directly work in that space, right? Because if you take gradients and stuff, you cannot exit this sum structure, right? So in particular, I think that if you try to, you could also ask, okay, I take the dual function which is defined as an element on the product, and you try to maximize that. Instead of assuming that it is factorized, you try to find the maximizer there. And I don't think that the maximizer looks like that. So I'm trying to understand if...
Actually...
For an estimate, I agree.
Precisely what he's saying. That like the two of
They're not the same.
For the same one, like the gradient ascent on the
It's something
with you
different.
is like it doesn't preserve the
Okay,
structure.
so we're only using that space to get a bound, forget the linear rate convergence somehow. But we're not really doing gradient ascent in that space.
Yeah,
Okay.
exactly.
Okay. Thank you.
Yeah, but actually I would argue that if you take the right gradient, you don't exit that space. But that's maybe detail. So for this, I would just want to take this inequality here and rewrite it as basically an inequality of the error of the dual functional. So now I want to look at quantities E of U and V, basically just the maximum of D minus D of U and V.
Max of D in which space?
Just the regular space we're dealing with. So basically this somewhere indicates how far we are from the optimal value for our dual functional. And basically rewriting this inequality here gives you that the error that we have at UN plus 1, Bn plus 1 is less or equal to the error at UN Bn. And then we subtract a constant times the norm squared of the block gradients. All right, but on the other hand, we want to make use of the strong concavity, and that gives E of U and V as less or equal to a constant times the square of the norm of the gradient on the space as defined there.
You mean at each step, right? So n+1.
I mean, this basically holds for all U and V as long as you have the spectral estimates for your operator that I just showed. So on the domain where this dual functional is strongly concave, you have this within suitable constant. But then I want to use this one up here. So one can bound this by the sum of the block gradients in the norm squared. And with that, we almost have everything we need. So if one combines this and that, one gets at E of UN plus 1, Vn plus 1. That's so equal to E of UN Vn minus some constant times E of UN plus 1 Vn. But initially we also said that we only improve when we make gradient steps. So one can also trivially bound this by the error that we have before making the second gradient step. So this quantity is certainly smaller than the minimum of these two. So it's also smaller than the minimum, so the maximum of the minimum of these two, taking all the values that are possible for E of UN plus 1 Vn. So I don't know where this is, but for these inequalities, it's somehow good if it's small, but it's also good if it's large. So there is an optimum or a worse situation in between. So one can bound this by 1 over 1 plus C7 E of UN Vn. And this is basically all we wanted, to have a linear rate of convergence, because now we see that we have a fractional part of our arrow in the dual functional that we take away in each double gradient step. And that's why we have linear convergence in the end for the values of the dual functional. But then we can also use the concavity again to translate this back to the convergence of the.
I didn't see how you move the last. They're not consecutive inequality. I think it is. The first one is right. The second one is also right. You use them all to get the third.
Yeah.
Okay, that's good.
So these
So and then
two.
yeah, exactly.
Okay. All right. So then we have linear convergence everywhere. And what you also get is that for the Sinkhorn algorithm, you also get a linear convergence rate, which is quite nice. So now I want to look at some practical experiments. So for this, I took just some numbers with no further structure, just some numbers to play with, just smallest non-trivial case possible, 2 times 2 marginals. And basically started at 0 and wanted to have a precision of 10 to the minus 8. And yeah, with the dual block gradient ascent algorithm, one gets a result after around 3,000 iterations. And this is basically how the dual functional evolves with the iterations. So it is pretty linear, I'd say. Also for the result, for the quantum state that we want to look at in the very end. And also if one considers the error of the first Kantorowicz potential U, or second, or the marginal error, it all converges quite linearly. I also did some experiments with the Sinkhorn algorithm, but there's a question.
Short question to what you compare the value of the dual function.
Okay, yeah. For these plots, I always compare it to basically the output of my algorithm.
Sorry?
I always compare it to the output of my algorithm.
Yeah, No, but you show the plot of convergence of error of the dual function. So this is some residual, right? Error of the dual function, yes.
Yeah.
It's like absolute difference of value of the dual functional with something.
Yeah, so it is the dual functional of the result that I get in the end by using this algorithm minus the dual functional of UI, VI.
Okay.
Does it make sense?
Okay, I understand.
Okay. Okay, so I'm almost at the end. Also for the Sinkhorn algorithm, you get a really nice straight line. And this time you only need 18 iterations. So in terms of numbers of iterations, it is significantly lower, the number of steps that you need to take. But yes.
How do you compute this?
Yeah, he's going to say it, I think.
Yeah. If there is a world where we have a closed formula for this argmax that we have in our Sinkhorn algorithm, the situation is quite nice, because then we have pretty fast convergence. But I'm not aware of any such formula. So I basically did, again, the most simple approach you could imagine. Again, and I basically just used gradient ascent again.
So do you just at every step for every u, let's say you apply gradient descent for u several times and you sort of converge to the argmax?
Exactly.
Okay.
So basically what you see here is you alternatingly almost have perfect marginals. So your gradients almost vanish. So gradients are the marginal errors. And if you plot it not iteration-wise, but gradient descent step-wise, you basically get this. So there's always, in each step of the Sinkhorn algorithm, you have a phase where you improve a lot, but then for some 1,000 iterations maybe of your gradient, your dual functional stays virtually unchanged. And that's why in the end you need a few iterations more. Also for the result. Of course, there are lots of things one can do to improve this. So this is just probably a start of tackling this problem algorithmically. But yeah, I've got some questions. So first of all, is there a better way to compute the differential of the matrix exponential? Because if one wants to have higher order methods, we would also need derivatives of the gradient, and then somehow this integral representation does not seem too nice for computational purposes to me. Also, computing partial traces of the matrix exponential would be nice. Maybe do some stochastic thing there. I don't know if that's feasible. Then moving to more general regularizations, how would you compute the derivative of these? And of course, can you get better spectral bounds than the one I presented? And then from a practical perspective, in all applications for regularized quantum optimal transport, what would you want to have as problem parameter? So how many Hilbert spaces or particles do you want? What are these dimensions? So do the problem parameters maybe have some additional structure? Also, what kind of regularizations are of interest from a practical perspective? And symmetry conditions, how important are they in practice? And what's the required position? And with that, I would like to thank you for your attention, and I'm happy to answer any question.